Tonight, we're going to look at something most people never think about when they picture space travel. The dangers that don't announce themselves. Deep space isn't just empty and cold, it's filled with threats that produce no light, no sound, and no warning of any kind before they strike. Radiation that passes through solid matter without a trace. Objects with no star to illuminate them. Gravity strong enough to bend a trajectory from millions of miles away. Every one of them, silent, undetectable, and none of it shows up until it's already too late to react. And by the end of tonight, you're going to understand exactly what these invisible traps are, how differently each one can end a mission, and why deep space travel means confronting all of them at once, with no way to know which one you'll encounter first. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Picture the space between stars. Most people imagine something like a vast, dark room. Empty, silent, cold. And in the most basic sense, that's correct. The interstellar medium, the technical name for the material that fills the space between star systems, is nearly empty by any standard we're used to on Earth. Out there, you might find one atom per cubic centimeter on average. One. The air in the room around you right now contains about 25 quintillion molecules per cubic centimeter. So yes, interstellar space is empty in the way that matters for breathing. But here's where people go wrong. Empty does not mean harmless. Empty does not mean passive. And empty certainly does not mean survivable. Because what fills that near vacuum isn't nothing. It's radiation at energies that our most powerful laboratories can barely reproduce. It's particles moving at velocities, approaching the speed of light, carrying kinetic energies that dwarf anything in ordinary human experience. It's gravitational fields so extreme they can tear matter apart at the molecular level without making contact with a physical surface. It's magnetic environments strong enough to fundamentally alter the structure of atoms themselves. It's sudden releases of energy so enormous that nuclear weapons look trivial in comparison, delivered at the speed of light with no possible advance warning. Deep space is not an absence of things. It's a presence of things you cannot see, cannot feel, and cannot survive without extraordinary technological protection. Every threat out there is invisible until the moment it isn't. And by then, in most cases, there is nothing to be done. Start with the most fundamental trap, the vacuum itself. You've heard that space is a vacuum, and you probably think you understand what that means. A place without air. A place where you'd suffocate. What you may not have thought through is the full physical reality of what your body is doing right now to stay alive, and what happens the moment the environment it requires is removed. At sea level on Earth, the atmosphere pushes in on every square inch of your body with about 14.7 pounds of force. That's what 1 atmosphere of pressure means. Spread across your entire body surface area, roughly 20 square feet for an average adult, that adds up to approximately 43,000 pounds of total force pressing inward on you from every direction. Over 20 tons of pressure. You don't feel it crushing you because your body pushes back with equal force from the inside. Every cell, every blood vessel, every organ is in pressure equilibrium with the atmosphere around it. Your cardiovascular system is calibrated to function at this pressure. Your respiratory system depends on it. The entire mechanism of breathing relies on pressure differentials between the inside and outside of your lungs. When you inhale, your diaphragm expands your chest cavity, lowering the pressure inside your lungs below the external atmospheric pressure, and air rushes in to equalize. When you exhale, you compress your chest, raising internal pressure above external, and air rushes out. The gases dissolved in your blood and tissues, oxygen, nitrogen, carbon dioxide, exist in chemical equilibrium that assumes atmospheric pressure as a constant baseline. Your body is a machine built around one atmosphere. Remove that pressure, remove it completely, instantly, the way space removes it, and every system in your body fails simultaneously. The gases dissolved in your blood behave like a soda bottle being opened. Pressure drops. Dissolved gases come out of solution. Bubbles form. Not in a glass of liquid. In your circulatory system. In your tissues. In the fluid surrounding your eyes and your joints and your organs. The medical term for this process is ebullition, the formation of gas bubbles in bodily fluids due to reduced external pressure. Your blood begins to foam. Your skin swells as subcutaneous gases expand. The moisture in your mouth boils not from heat, but because at near zero pressure, the boiling point of water drops to body temperature. Water's boiling point is not a fixed number. It depends on external pressure. At sea level, it's 212 degrees Fahrenheit, or 100 degrees Celsius. At the top of Mount Everest, where atmospheric pressure is about a third of sea level, water boils at around 154 degrees Fahrenheit, or 68 degrees Celsius. In the near vacuum of space, the boiling point drops to 98.6 degrees Fahrenheit, or 37 degrees Celsius. Your body temperature. Your saliva boils on your tongue. The moisture in your lungs begins to flash into vapor. The fluid on the surface of your eyes evaporates. These aren't theoretical predictions. They've been observed in vacuum chamber experiments with liquid water. Flash, boiling at room temperature. The same physics applied to the fluids in a human body. There is a documented case from 1965. A technician at Johnson Space Center was testing a spacesuit in a vacuum chamber when the suit suffered a pressure failure. He was exposed to near vacuum conditions for approximately 14 seconds before the chamber could be repressurized. He reported that the last thing he remembered before losing consciousness was feeling the saliva on his tongue begin to boil. He recovered fully because the repressurization was immediate and medical attention was provided within seconds. 14 seconds. That's the documented upper limit of survivable vacuum exposure under the most favorable possible conditions with instant repressurization and immediate medical response. In actual deep space, there is no chamber to repressurize. There is no rescue team at a control panel 40 feet away. The vacuum extends in every direction for trillions of miles. 14 seconds becomes the end of the story, and that's not a figure of speech. The timeline of what happens to a human body in vacuum has been assembled from animal experiments in decompression facilities, from the documented case records of accidental exposures, from the known physiology of pressure and blood chemistry, and from the physics of gases in solution. At 0 seconds, exposure begins. Pressure drops from 1 atmosphere to near zero instantly. If you were holding your breath, the gas in your lungs begins to expand. The volume of a gas is inversely proportional to pressure, so at near zero pressure, the gas in your lungs would expand without limit. Lung tissue begins to tear. This is why training for decompression accidents emphasizes exhaling immediately. If you exhale, the gas can escape. If you hold your breath, the expanding gas tears the lung from the inside out. At 1 to 2 seconds, embolism is underway in earnest. Dissolved gases are leaving solution throughout the circulatory system and tissues. Gas bubbles are forming in your blood, in the synovial fluid of your joints, in the tissue surrounding your organs. Your skin begins to swell as subcutaneous gases expand. The moisture on your eyes is evaporating. Your saliva is boiling on your tongue. At 4 to 6 seconds, the evaporative cooling from boiling moisture in your mouth and nasal passages creates a brief sensation of cold. Your skin is visibly swelling. Your body would appear bloated to an external observer. At 8 to 10 seconds, oxygen levels in your bloodstream have dropped far below the threshold required for brain function. Your circulatory system, full of gas bubbles, is no longer delivering oxygen, effectively even to the tissues that still have it. Vision is narrowing. Hearing is fading. At 12 seconds, consciousness is gone. At 30 seconds, the cardiovascular system is in complete disarray. The heart may still be beating in some form, but it is pumping foam through vessels that are failing. At 60 seconds, permanent neurological damage from oxygen deprivation is certain. Even if repressurization were instantaneous at this point, full neurological recovery would be impossible. At 2 minutes, clinical death. No cardiac output. No brain activity. No return. This is the vacuum, not an abstract concept. A specific, physical, documented mechanism of physiological failure, operating on a time scale measured in seconds. 14 seconds to unconsciousness. 2 minutes to the end. With no countermeasure except the maintenance of atmospheric pressure continuously, without interruption, for the entire duration of the voyage. Now, step inside the spacecraft. Sealed, pressurized, alive. You've solved the vacuum problem. You're still in deep space. And what's moving through that vacuum is where the hazards become genuinely complex. Start with the local source, the Sun. Our star produces energy by fusing hydrogen into helium in its core, releasing approximately 3.8 times 10 to the power of 26 joules per second. On the surface of Earth, we receive only a tiny fraction of that output. The rest radiates in all directions into space. What reaches Earth is further filtered by the atmosphere. Ultraviolet radiation, X-rays, and gamma rays are largely absorbed before reaching the ground. Charged particles in the solar wind are deflected by Earth's magnetic field. In space, neither filter exists. The solar constant, the energy flux from the Sun at Earth's orbital distance, is about 1,361 watts per square meter. That's the full spectrum, nothing removed. The visible light portion of that is what drives photosynthesis on Earth. But the ultraviolet portion causes DNA damage. On Earth, the ozone layer absorbs the most energetic UVC band entirely, and most UVB. In space, there's no ozone. All UV wavelengths hit. Ultraviolet radiation damages DNA by forming abnormal bonds between adjacent nucleotide bases in the double helix. These pyrimidine dimers, as they're called, distort the structure of the DNA molecule. If not repaired before the cell divides, they can cause mutations. With sustained exposure, those mutations accumulate. The probability that one of them initiates cancer is real and measurable. Above ultraviolet in the energy spectrum sit X-rays and gamma rays. These penetrate tissue far more deeply. They ionize atoms throughout the body's interior, not just at the surface. The sun produces X-rays and gamma rays continuously at low levels and in enormous bursts during solar flares and coronal mass ejections. A major solar flare releases as much as 10 to the power of 25 joules in a matter of minutes. The electromagnetic radiation from the flare X-rays and gamma rays reaches Earth's orbital distance in 8 minutes. It arrives simultaneously across the entire sunward hemisphere of Earth or of a spacecraft in transit. Following the electromagnetic burst, a wave of highly energetic charged particles, protons, electrons, heavier ions follows. These particles travel slower than light, so they arrive minutes to hours after the electromagnetic radiation, depending on their energy and the geometry of the flare. This small window, the gap between the electromagnetic arrival and the particle arrival, is the warning time that mission controllers use to get astronauts to shelter. For astronauts on the International Space Station, the station's position within Earth's magnetosphere reduces the peak particle flux significantly. Combined with designated storm shelters, areas with additional shielding within the station, this provides reasonable protection against all but the most extreme events. For crews in transit to Mars or beyond, in open space without the magnetosphere's protection, the situation is different. The full particle flux arrives. There is no magnetosphere to deflect any of it. The shielding of the spacecraft hull provides some protection against lower energy particles. Against the highest energy particles in a major solar particle event, the hull is nearly transparent. During the Apollo program, astronauts traveling to and from the Moon were beyond the protection of Earth's magnetic field. The scientific and medical community at the time was well aware of the solar radiation risk. The Apollo missions were timed relative to the solar activity cycle and individual solar conditions. Every mission had contingency plans for solar particle events. No major events occurred during the brief periods when astronauts were on the lunar surface or in transit. That was luck, not engineering, not design. Luck. For missions lasting months or years, relying on luck is not a planning strategy. The probability of encountering a significant solar particle event during a 2-year Mars transit mission at typical levels of solar activity is not small. It's roughly 1 in 3 for a major event and considerably higher for moderate events. The design challenge is that the shielding required to provide meaningful protection against the most energetic solar protons is extremely massive. It's the same mass problem that appears everywhere in spacecraft design. Every kilogram of shielding must be launched from Earth. Every additional kilogram requires additional fuel. The fuel itself adds mass. The trade-off between shielding mass and acceptable radiation dose is one of the central design challenges for any crewed deep space mission. There is no solution that provides complete protection within the mass budget of a practical spacecraft. There is only the selection of what risk level is acceptable and the design of the best achievable mitigation within the constraints. But the Sun is a single star and a relatively well-behaved one. The universe contains hundreds of billions of stars in our galaxy alone, and roughly 2 trillion galaxies. Every energetic event in every one of those systems has sent radiation and particles outward. Most of it dissipates and becomes negligible across the distances involved. But some of it, the most energetic products of the most violent events, travels across the entire galaxy and arrives at your location with its energy barely diminished. That's galactic cosmic rays. And galactic cosmic rays are in a completely different category from solar radiation. A galactic cosmic ray is an atomic nucleus moving at close to the speed of light. Mostly protons and helium nuclei, but including all the heavier elements as well: carbon, oxygen, silicon, iron stripped of their electrons and accelerated by the most violent events in the universe. The acceleration mechanism is most clearly understood for supernova remnants. When a massive star ends in a supernova, the expanding shockwave accelerates particles in a process called diffusive shock acceleration. Particles bounce back and forth across the shockwave boundary, gaining energy with each crossing until they reach velocities approaching the speed of light and escape the remnant into the interstellar medium. Neutron stars and black holes contribute additional particles through magnetospheric processes and accretion disk dynamics. Active galactic nuclei, the supermassive black holes at the centers of some galaxies that are actively feeding on surrounding material, produce the highest energy cosmic rays we observe. The most energetic cosmic rays ever detected carry about 10 to the power of 20 electron volts. That's about 16 joules of energy in a single subatomic particle. The Large Hadron Collider at CERN accelerates protons to roughly 6.8 times 10 to the power of 12 electron volts per proton at its highest operating energy. The most energetic cosmic rays carry about 10 million times more energy than the most powerful particle accelerator humans have ever built, concentrated in a single proton. These particles have been traveling through the galaxy for millions of years, scattered and deflected by galactic magnetic fields, but retaining most of their energy. When they hit the Earth's upper atmosphere, they produce showers of secondary particles that cascade downward through the atmospheric column. By the time those secondaries reach the surface, most of the energy has been dissipated. What reaches you on the ground is a small fraction of what came in. In space, there's no atmosphere. The primary particle hits whatever is in its path directly. And when it hits human tissue, the interaction is not gentle. A cosmic ray proton, at 90% of the speed of light, carries enough momentum that it tears through matter along its path, ionizing atoms as it goes. The ionization track, the trail of damaged molecules left behind, can extend through the entire width of the human body. Along that track, DNA molecules are shattered. Proteins are disrupted. Cell membranes are compromised. The ionization also ejects secondary electrons from the atoms it hits. These secondary electrons have enough energy to cause additional damage to surrounding tissue, spreading the damage laterally from the primary track. A single galactic cosmic ray particle can damage dozens or hundreds of cells along its path. Your body's repair machinery handles most of this. It has to. You're being hit by cosmic rays on the ground, constantly, in small but measurable numbers. The DNA repair pathways in your cells are continuously working to fix strand breaks, remove damaged bases, and restore the integrity of the genome. In space, the flux is much higher. Astronauts on the International Space Station receive radiation doses from cosmic rays approximately 150 to 200 times higher than people on the ground. This is despite the partial protection of Earth's magnetic field, which deflects a significant fraction of the lower energy cosmic rays before they reach orbital altitude. At higher energies, the magnetic field provides less deflection, and the most energetic galactic cosmic rays arrive at essentially full flux even inside the magnetosphere. Beyond the magnetosphere in open space, the lower energy galactic cosmic rays that the magnetic field was blocking now arrive as well. The total cosmic ray dose in open interplanetary space is higher than in low Earth orbit. For a Mars transit mission lasting 18 to 24 months, NASA's models predict that crew members would receive cumulative radiation doses that increase lifetime cancer risk by approximately 5% above baseline. 5%. That's the central estimate for acceptable risk in a Mars mission, based on current NASA guidelines for career radiation limits. But Mars is close. It's the nearest planet with any prospect of human habitation, and the transit requires crossing only a fraction of the solar system. Missions to the outer planets, Jupiter, Saturn, and beyond would require years of transit time. At the same cosmic ray flux, the accumulated dose scales linearly with time. 2 years gives 5%. 4 years gives 10. 10 years gives 25. The cancer risk doesn't plateau. It accumulates for as long as the exposure continues. And cancer is the risk we know about and can quantify. The neurological effects are what mission planners find more difficult to model. Studies using particle beams to simulate galactic cosmic ray energies and types have exposed rodent subjects to doses comparable to what they'd receive in multi-year deep space missions. The results show measurable changes in brain function, reduced performance on memory tests, impaired spatial reasoning, changes in fear and anxiety responses, changes in the density and connectivity of neural circuits in the hippocampus and prefrontal cortex, the brain regions most involved in the kinds of complex decision-making a deep space crew would need to perform continuously. Whether these effects translate to humans at the doses and timescales of an interstellar or even an outer solar system mission is not known. The animal data suggests reason for concern. The human data doesn't exist yet, because no human has been in the radiation environment of deep space for long enough. The first crews to attempt long-duration deep space missions will be generating that data. They are the experiment. The results will inform the design of later missions. This is how exploration has always worked. But it means that the first crews are accepting unknowns that later crews won't face. That's a specific, defined additional risk that comes with being first. Shielding against galactic cosmic rays is one of the genuinely hard engineering problems in human spaceflight. Not hard in the sense that the solution exists and is expensive. hard in the sense that the physics actively resists the obvious approach. You'd expect that adding more material between the crew and space would reduce their radiation dose. For solar radiation and for lower energy particles, this is true. For high-energy galactic cosmic rays, the relationship is more complex. When a high-energy cosmic ray hits a massive nucleus iron, aluminum, the structural metals of spacecraft, it can fragment that nucleus in a process called nuclear spallation. The fragments spray out in a cone, each carrying a fraction of the original energy. Some of those fragments are lighter nuclei. Some are neutrons, which are particularly biologically damaging because they have no charge and can penetrate cells and interact with nuclei directly. If the spacecraft wall is made of heavy materials, the cosmic ray that enters as a single proton might emerge from the wall as a shower of protons, neutrons, and heavier fragments, each capable of causing biological damage. In some configurations, thick metal shielding produces a higher effective radiation dose inside the spacecraft than thin or no shielding would. This counterintuitive result comes from the physics of nuclear fragmentation. The solution is to use hydrogen-rich materials. Hydrogen nuclei, single protons, produce far fewer dangerous secondaries when struck by cosmic rays. Water and polyethylene are effective shielding materials for this reason. But the mass required to provide meaningful protection is enormous. A spherical shell of water, 2 meters thick, surrounding a crew compartment, would weigh hundreds of thousands of kilograms. The economics of launching that mass are prohibitive with any propulsion system we currently have. Some mission architectures propose using consumable water, water carried for drinking, and other uses as incidental shielding. The water has to be carried anyway. Routing it through walls and locating it strategically around sleeping quarters and radiation storm shelters provides some benefit without adding dedicated shielding mass. But the total amount of water a crew consumes over months or years is a small fraction of what would be needed for effective cosmic ray shielding. It helps at the margins. It doesn't solve the problem. Other proposals involve active magnetic shielding, generating a strong magnetic field around the spacecraft to deflect incoming charged particles, the way Earth's magnetosphere deflects the solar wind. The physics works in principle. The engineering is extremely challenging. The magnetic field would need to extend tens of meters around the spacecraft. Generating and maintaining such a field requires enormous power. The field would deflect protons and other charged particles, but neutral particles, certain secondary particles and neutrons would be unaffected. And the hardware required superconducting coils, cryogenic cooling systems, power generation and storage adds its own mass. Every approach to cosmic ray shielding either fails to work as well as hoped, requires mass that exceeds practical limits, requires power that exceeds available generation, or some combination of all three. This is the current state of the problem. There are research programs working on all of these approaches. Progress is being made. But there is no solution on the horizon that resolves the cosmic ray challenge for long-duration crewed missions. It remains an open problem, not one that will prevent us from going, but one that will make going more dangerous than the publicity materials usually acknowledge. Magnetars. If galactic cosmic rays are the chronic hazard of deep space always present, slowly accumulating their damage. Magnetars represent the acute hazard. The sudden release of staggering energy from a compact object with no practical warning. A magnetar is a type of neutron star. To appreciate what makes a magnetar different from an ordinary neutron star, start with what a neutron star is. When a massive star between roughly 8 and 20 times the mass of the Sun exhausts its nuclear fuel, the iron core that accumulates at the end of the fusion sequence collapses. The collapse happens in about a second. A sphere, roughly the size of Earth, compresses to a sphere about 12 miles across. The density reaches nuclear density about 400 million tons per cubic centimeter. Electrons and protons are forced together into neutrons. The result is a neutron star, an object with more than a solar mass packed into a volume smaller than a city. Neutron stars already possess extraordinary magnetic fields. Ordinary neutron stars have magnetic field strengths in the range of 10 to the power of 8 to 10 to the power of 12 teslas. For comparison, the strongest continuous magnetic field ever produced in a laboratory is about 45 teslas. An ordinary neutron star has a magnetic field roughly 2 million to 40 billion times stronger than our best laboratory magnets. Magnetars are neutron stars, where the magnetic field is even more extreme, formed from rapid rotation during the collapse, or from dynamo processes in the convective neutron star interior in the first seconds after formation. Magnetar fields reach 10 to the power of 10 to 10 to the power of 11 teslas. At these field strengths, the quantum mechanical structure of atoms changes. Electrons cannot maintain their normal orbital configurations. They are squeezed into cylinders aligned with the field lines. The chemistry of ordinary matter becomes impossible in the immediate vicinity of a magnetar. Molecules as we understand them do not exist near one. Magnetars are unstable. Their enormous magnetic fields slowly decay, releasing energy in the process. This decay is not smooth. It happens in sudden releases, starquakes, as the magnetic field restructures, producing bursts of X-ray and gamma radiation. The scale of these events varies enormously. Smaller flares release roughly 10 to the power of 38 to 10 to the power of 40 joules. Giant flares, the rarest and most extreme events, release on the order of 10 to the power of 46 joules. The December 27, 2004 event from SGR 1806 to 20 was a giant flare of this magnitude. The burst lasted about 0.2 of a second. In that time, it released more energy than the Sun emits in about 250,000 years. SGR 1806 to 20 is approximately 50,000 light-years from Earth. The burst was detected by gamma-ray satellites in orbit, and it saturated their instruments. It ionized Earth's upper atmosphere, briefly compressing the ionosphere by several miles. It disrupted radio communications from 50,000 light-years away. The scaling to closer distances is direct mathematics. Energy flux scales with the inverse square of distance. At 5,000 light-years, still an enormous distance, completely uncrossable on human timescales, with any current technology, the energy flux reaching Earth from an equivalent event would be 10,000 times higher than what was received from SGR 1806 to 20. At 500 light-years, it would be 10 million times higher. At 50 light-years, it would be 100 billion times higher. The energy reaching Earth's orbit at 50 light-years from a magnetar giant flare comparable to SGR 1806-20 would be sufficient to destroy the ozone layer on the sunward hemisphere. Surface ultraviolet radiation would increase dramatically and remain elevated for months. The effects on complex life, which evolved in an environment where the ozone layer was always present, would be severe. The nearest known magnetar to Earth is currently estimated to be about 9,000 light-years away. This is considered a comfortable distance. But the galaxy contains roughly 1 billion neutron stars. The fraction that are magnetars at any given time is uncertain. The fraction of those magnetars that are in active phases capable of giant flares is uncertain. The prior history of magnetar activity in our galactic neighborhood over the past 100 million years is not known. We identify magnetars when they produce detectable flares because quiescent magnetars are difficult to observe. There may be active magnetars we haven't yet catalogued. There may be magnetars that have been quiescent for thousands of years but are capable of giant flares. The landscape is not fully mapped. And for a crew traveling in deep space, the invisibility of the threat is the defining characteristic. Gamma radiation travels at the speed of light. The burst and the warning arrive simultaneously. By the time your instruments detect the burst, the radiation front is already at your position. There is no early warning. There is no response. If the geometry is wrong, if your spacecraft is oriented facing a magnetar when it produces a giant flare, the outcome is determined in the first fraction of a second. The shielding on any practical spacecraft is not designed for that energy scale. It couldn't be, within any mass budget we might contemplate. The only protection is distance, not being in the beam. And the only way to guarantee that is to know where all the active magnetars are and what trajectories their beams sweep. We don't know that. We can't know that. With current astronomical capabilities, for any level of assurance that would be adequate for mission planning. Magnetars are invisible traps in the most literal sense. You can't always see them. You can't always know they're active. And if they're pointed at you, you don't know until you're already in the radiation front. Pull back and consider gravity on the most extreme scales. Gravity is the weakest of the four fundamental forces by a large margin. Electromagnetism is roughly 10 to the power of 36 times stronger at subatomic scales. But gravity has a property that the other forces lack. It accumulates. There's no negative gravity. You can't cancel it. Every mass in the universe adds to the total gravitational field, and all those contributions point in the same direction toward the mass producing them. At the scales of ordinary matter, people, buildings, mountains, this weakness means gravity is easy to overcome. You can pick up a book against Earth's gravity with negligible effort. Electromagnetism in your muscles overcomes the gravitational pull of an entire planet. But at the scale of compact stellar remnants, neutron stars, and black holes, the accumulated gravity of a solar mass, or more, compressed into a tiny volume, produces field strengths that nothing familiar can resist. Near these objects, gravity creates effects that don't exist anywhere in normal human experience. The most visually striking is spaghettification. Near a sufficiently compact, massive object, the gravitational field varies significantly across the length of a human body. The difference in gravitational acceleration between your head and your feet, tiny and imperceptible on Earth's surface, becomes enormous near a compact object. This difference is a tidal force. Near a stellar mass black hole, say, a remnant with 15 solar masses compressed into a sphere about 55 miles across the tidal force differential across a 2-meter human body, at the event horizon is approximately 10 billion times the gravitational acceleration you feel on Earth's surface. Your feet are being pulled toward the black hole with a force 10 billion times your weight more than your head. The effect is not subtle. Every molecular bond in your body that maintains structural integrity along the gravitational gradient fails. Your body is being pulled apart. At the same time, conservation of volume means you're being simultaneously compressed in the perpendicular directions, elongated along the gradient, compressed across it, stretched and thinned into a thread of matter, as the name implies. This happens well before you reach the event horizon of a stellar mass black hole. For a 15 solar mass black hole, the tidal forces become catastrophically lethal for a human body at a distance several times the event horizon radius. You'd be torn apart in open space. Not because you hit anything, not because any surface is nearby, simply because the gradient of gravity across your body is stronger than the forces holding your body together. For supermassive black holes, millions to billions of solar masses, the situation reverses. The event horizon radius scales with mass. A billion solar mass black hole has an event horizon diameter of about 3 billion miles. At that scale, the tidal force differential across a 2-meter human body at the event horizon is actually quite small. You might cross the event horizon without experiencing catastrophic tidal forces. You'd be inside the event horizon. No path leads out. No signal from inside reaches the outside universe. What happens to matter inside the event horizon is a question that general relativity cannot fully answer, because the singularity at the center of a non-rotating black hole, or the ring singularity at the center of a rotating one, represents a mathematical breakdown of the equations. Infinite curvature, infinite density. These infinities are almost certainly telling us that our theory is incomplete. Not that infinities literally exist in nature. A complete theory of quantum gravity would describe what actually happens at these scales. We don't have that theory yet. It's one of the most important open problems in theoretical physics. What's not unknown is the navigational hazard. An isolated stellar mass black hole that's not actively accreting material from a companion star emits nothing detectable from a reasonable observing distance. No light, no radio waves, no infrared, no thermal radiation, just a slight gravitational distortion of space-time in its vicinity. To detect a quiet, isolated black hole at a distance of light hours, you'd need to either notice the gravitational anomaly in your own trajectory, which requires extremely sensitive accelerometers and very precise trajectory modeling, or detect the gravitational lensing of background light sources, which is subtle and requires sustained observation and analysis. Neither method gives you a lot of warning time at interstellar cruise velocities. By the time you've confirmed there's something massive ahead, the distance to it may already be small enough that course correction requires more thrust than your engines can deliver. The trap is not the black hole. The trap is the silence. The absence of any announcement. The fact that the deadliest thing in the immediate vicinity might be the thing you can't detect. Between the stars, the hazards become even more varied. The interstellar medium itself becomes a threat at the velocities required for practical interstellar travel. Consider what 10% of the speed of light actually means. It's 18.6 million miles per hour. A spacecraft traveling at that speed would cross the diameter of Earth in about 1/45th of a second. It would travel from New York to London in about 1/200th of a second. At this speed, the interstellar medium, sparse as it is no longer negligible. The relevant quantity is kinetic energy, and kinetic energy scales with the square of velocity. At 10% of light speed, the kinetic energy of a hydrogen atom in the spacecraft's reference frame is about 47 mega-electron-volts. That's the energy of a particle in a reasonably powerful particle accelerator. In the frame of the spacecraft, each hydrogen atom the vessel encounters is hitting it with the energy of an accelerated particle. There are roughly 1 atom per cubic centimeter in the interstellar medium. Over a travel distance of 4 light-years at 10% of light speed, the total number of atoms intersecting a 1 square meter cross-section of the spacecraft's leading surface is approximately 1.2 times 10 to the power of 25. That's 12 septillion individual particle impacts on a 1 square meter surface. Each impact deposits some energy. Individually, each impact is tiny. Cumulatively, over the journey, the total energy deposited in the leading surfaces is substantial. The leading surface heats. It erodes. Material is ablated away. Any practical interstellar spacecraft would need dedicated ablative shielding at the front material designed to gradually wear away, protecting the structure behind it at the cost of the shield itself. The thickness of that shield depends on the medium density, the travel velocity, the material properties, and the acceptable erosion rate. For a 40-year voyage at 10% of light speed to the Alpha Centauri system, the shield mass required is a genuine engineering problem that existing analysis suggests would be significant. And the hydrogen gas is the baseline case. The interstellar medium also contains helium, which is heavier and deposits more energy per impact. It contains free electrons. It contains ionized atoms. It contains dust grains. The dust grains range from nanometers to micrometers in size. At 10% of light speed, a silicate dust grain, 1 micrometer in diameter, barely visible under an electron microscope, carries kinetic energy roughly equivalent to a large firecracker. It doesn't just deposit energy at the surface. It punches through surface layers, converting itself and whatever it hits into plasma, sending a jet of hot material deeper into the shield. A grain, 10 micrometers across, still invisible to the naked eye, carries energy equivalent to a substantial explosive. A grain, 100 micrometers across about the thickness of a human hair, hits with the energy of several kilograms of TNT. There is no material that survives these impacts intact. The shield absorbs them, converts the energy to heat and ablated vapor, and gradually wears away. How fast it wears depends on the dust density along the route. The dust density in the interstellar medium is not uniform. It varies by region, by proximity to star formation zones, by the history of supernovae in the area. We have statistical models of average interstellar medium properties, but we cannot predict the specific dust density along any specific travel path with the precision that mission planning would require. The engineer has to design for worst-case scenarios within the range of plausible environments. That means designing conservatively, which means more shield mass, which means more propulsion requirements, which means more everything. The chain of engineering consequences from interstellar medium interactions runs through the entire design of any practical interstellar vessel. Then there are the macroscopic objects. The interstellar medium isn't just gas and dust. It contains larger objects, rogue planets, captured comets, bodies ejected from forming planetary systems over the past 5 billion years. In 2017, astronomers detected an object moving through the inner solar system on a hyperbolic trajectory, meaning it was not gravitationally bound to the Sun and had come from interstellar space. This object, designated Oumuamua, was the first confirmed interstellar visitor we'd ever observed. It was elongated, or possibly disc-shaped, perhaps several hundred meters in its longest dimension. It had a reflectivity and spectrum unlike any known solar system object. It passed through and left, continuing its journey through interstellar space. In 2019, a second interstellar object was detected, Borisov, a comet-like body roughly half a mile across. 2 interstellar visitors detected in 3 years from astronomical surveys that are not designed to find them and don't have complete sky coverage. That observation rate implies that the interstellar medium contains far more objects of this type than we previously assumed. Estimates based on the detection rate suggest that interstellar objects like Oumuamua might outnumber the stars in our galaxy, trillions of them drifting through the space between stellar systems. For an interstellar spacecraft, these objects are invisible until they're close. They reflect no starlight because they're far from any star. Their thermal emission is too faint to detect at interstellar distances. Their gravitational influence on a spacecraft trajectory is imperceptible until the encounter distance is very small. At 10% of light speed, a spacecraft covers about 3 million miles per minute. An object detected at a distance of about 3 million miles, roughly 13 times the distance from Earth to the Moon, gives the spacecraft about 1 minute of warning time. At 10% of light speed, the thrust required to change trajectory enough to avoid a half-mile object in 1 minute is many orders of magnitude beyond any propulsion system anyone has seriously proposed. The practical reality is that collision avoidance for macroscopic objects at relativistic velocities is not achievable with any technology in the conceivable near-term future. The shielding approach, carrying enough material at the front of the spacecraft to absorb the impact, works for dust and small particles. For objects larger than a few centimeters, the kinetic energy at 10% of light speed exceeds what any shield can absorb without catastrophic structural failure. A rock 10 centimeters across, hitting at 10% of light speed, carries roughly the kinetic energy of a 10-kiloton nuclear explosion. There is no spacecraft hull that survives that. The probability of hitting a 10-centimeter rock on any given voyage is low. The interstellar medium, even with all its invisible objects, is mostly empty. But mostly empty across 4 light-years still leaves some probability of a catastrophic encounter. Calculating exactly what that probability is requires knowing the size distribution of interstellar objects with far more precision than current observations can provide. The uncertainty in that probability is itself a risk. We don't know how likely a catastrophic impact is on an interstellar voyage. We know it's not zero. And for a mission where the crew has no ability to return and no rescue is possible, not zero has a different weight than it does in more forgiving environments. The quantum mechanical properties of space-time add one more layer to the deep space threat environment. In 1974, Stephen Hawking published a result that genuinely surprised theoretical physicists. He demonstrated, using a calculation that combined general relativity with quantum field theory, that black holes emit radiation. Before Hawking's work, the general understanding was that nothing escapes from a black hole. The event horizon was a one-way membrane. Light and matter could fall in, but nothing could come out. Hawking showed that quantum mechanics changes this picture at a fundamental level. The quantum vacuum is not truly empty. It fluctuates. Virtual particle-antiparticle pairs continuously pop into existence from those fluctuations, briefly exist, and then annihilate each other, returning the borrowed energy. This process happens everywhere in space, continuously. It's normally undetectable. But near an event horizon, the situation changes. If a virtual pair forms with one particle just inside the horizon and its partner just outside, the inside particle cannot cross back out. It falls inward. Its partner outside becomes a real particle. It carries energy away from the vicinity of the black hole. To a distant observer, the black hole appears to emit thermal radiation. The temperature of this Hawking radiation depends on the curvature of the horizon on the inverse of the black hole's mass. For astronomical black holes, the temperatures are extraordinarily low. A black hole with the mass of the Sun emits Hawking radiation at about 60 nanokelvins. A black hole with the mass of a typical stellar remnant, 10 solar masses, emits at 6 nanokelvins. For any black hole that forms by stellar collapse, Hawking radiation is undetectable in the current universe. The cosmic microwave background at 2.7 Kelvin drowns it out completely. These temperatures are so cold that the radiation is irrelevant on any practical timescale. But the mathematical machinery producing Hawking radiation doesn't apply only to black holes. It applies to any space-time geometry that creates a boundary with the causal properties of a horizon. Any region where signals from one side cannot propagate to the other. This is the point at which Hawking radiation becomes relevant to the question of deep space travel. Theoretical proposals for faster-than-light travel using space-time geometry, contracting space in front of a spacecraft and expanding it behind, creating a region in which the craft moves without itself accelerating, produce structures that have horizon-like boundaries. The leading edge of such a structure creates a causal boundary. No signal from ahead of the structure can propagate back into the interior. And wherever that causal structure exists, the Hawking mechanism applies. The radiation produced is not negligible for a rapidly moving structure. Calculations suggest that the effective Hawking temperature at the leading boundary of a superluminal spacetime structure could be extremely high, potentially high enough to destroy any biological crew inside. The faster the structure moves relative to an external frame, the more extreme the curvature of the boundary, and the higher the radiation temperature. This creates a deeply uncomfortable situation for proposals involving extreme space-time engineering. The very speed that makes the concept potentially useful. The ability to cross interstellar distances in reasonable timeframes is the same speed that drives the Hawking temperature of the Marnin, leading boundary to levels that destroy the crew. Physics has placed a radiation trap specifically inside the geometry of the most advanced propulsion concepts theorists have imagined. The question of whether there's a way around this cannot be answered with current theory. It requires a complete theory of quantum gravity, the still unknown framework that reconciles general relativity with quantum mechanics, and we don't have one. What is known is that subluminal versions of the same concept, space-time structures, moving below the speed of light, don't form true horizons. The causal boundary condition that triggers the Hawking mechanism requires superluminal motion. Below light speed, no horizon forms. The radiation problem doesn't arise in the same form. This is one of the reasons serious researchers in the field focus on subluminal geometries rather than superluminal ones. Not because superluminal travel is less appealing, because the physics of superluminal space-time structures may be inherently self-defeating for biological travelers. The trap is inside the tool, and it may not be removable. Now consider the human body itself, not as a target for external hazards, but as a system that breaks down in the absence of things it requires. Gravity. Every human who has ever lived on Earth has experienced a constant gravitational acceleration of 9.8 meters per second squared, directed downward every moment of their existence. The human body was shaped by that constant. The skeleton is sized and structured to support the body's weight against it. The cardiovascular system pumps blood upward against it. The organs of balance in the inner ear detect it and use it as the primary reference for orientation. Your posture, your gait, your reflexes, your bone density, your muscle mass, all calibrated to a world where down is a constant direction and gravity is never absent. In microgravity, the adaptation reverses. Within the first day or two of weightlessness, fluids that gravity normally keeps in the lower body, in the legs, the abdomen shift upward. The face becomes puffy. The legs thin. The sinuses fill. There's a persistent sensation of head pressure, as if you're perpetually leaning forward. This fluid shift is not just uncomfortable. It changes the mechanical environment of the brain. Intracranial pressure increases slightly. The shape of the eyeball changes. The optic nerve sheath, the tissue surrounding the nerve that connects the eye to the brain, may become compressed. In some astronauts, these changes are associated with changes in visual acuity. The syndrome is now documented under the name Spaceflight-Associated Neuroocular Syndrome, or SANS. It doesn't affect all astronauts, and the degree of effect varies. But for those it affects significantly, it represents a genuine medical concern for mission planning. If a crew member on a long-duration deep space mission develops significant vision changes, their ability to perform critical tasks is compromised. And there's currently no medical intervention proven to prevent or reverse it during the mission. Below the neck, The cardiovascular effects of microgravity become apparent within days. The heart, no longer pumping blood upward against gravity, adapts by reducing its output. Cardiac output decreases. The heart itself can shrink slightly. Arterial walls change their stiffness properties in response to reduced loading. When astronauts return to gravity after long-duration missions, many experience orthostatic intolerance or difficulty maintaining blood pressure when standing up, leading to lightheadedness or brief loss of consciousness. This adaptation takes weeks to months to reverse after returning to Earth. For a crew landing on a planet after years in microgravity, the ability to function in even low gravity is temporarily impaired. The musculoskeletal system undergoes its own deterioration. Without mechanical loading, bones lose density at roughly 1 to 2% per month in the weight-bearing skeleton. Without the resistance of gravity, muscles atrophy. Astronauts, on long-duration ISS missions, are required to exercise approximately 2 hours per day, specifically to counteract these effects. The exercise regimens have improved significantly over the decades of continuous human presence on the station, and recent long-duration missions have returned crew members with less bone density loss than earlier missions of the same duration. But even with the best current countermeasures, some loss occurs. Over a multi-year voyage, the cumulative bone density loss would be significant. The fracture risk on arrival at a destination with any appreciable gravity could be serious. And all of these effects happen simultaneously with radiation exposure, with sleep disruption from the absence of a natural day-night cycle, with the psychological effects of isolation and confinement, and with the neurological effects we discussed from cosmic rays. In deep space, you're not managing one hazard at a time. You're managing the simultaneous interaction of many, each one interacting with the others. Radiation, impairing the body's repair mechanisms, at the same time as microgravity is suppressing bone formation. Psychological stress from isolation and confinement, elevating cortisol, which accelerates bone loss. Sleep disruption from the absence of natural light cycles, impairing cognitive function and immune response. These aren't additive. They interact. And the interactions, in some cases, make each effect worse than it would be in isolation. The human body, in deep space, is being asked to perform at high levels in an environment where every system it relies on is simultaneously under stress. For short missions, the body adapts and then recovers. For missions lasting years, the accumulation matters in ways we don't yet fully understand. Here's what time dilation adds to this picture. Einstein's special theory of relativity predicts, and experiments have confirmed, that time passes differently for objects in relative motion. Moving clocks run slow. The faster you move relative to an observer, the more slowly your clock ticks from that observer's perspective. This is not a theoretical curiosity. It's been measured directly. In the 1970s, atomic clocks were flown on commercial aircraft and compared to identical clocks left on the ground. The airborne clocks ran slightly slow, exactly as relativity predicts. GPS satellites must incorporate relativistic corrections. If they didn't, the satellite clocks would drift relative to ground clocks, and GPS accuracy would degrade rapidly. The correction is applied continuously. Time dilation is real, measured, and well understood. For an interstellar spacecraft traveling at 10% of light speed, the time dilation factor is about 0.995. The crew's clocks run at 99.5% the rate of clocks back on Earth. Over 40 years. That's about 2 months of difference. Small, but real. At 50% of light speed, the factor is about 0.87. The crew ages at 87% the rate of people they left behind. At 90% of light speed, the factor is about 0.44. The crew ages at less than half the rate of Earth. These numbers matter for deep space hazards because of a specific effect on the radiation environment. When a spacecraft moves at relativistic velocity, the particles it encounters don't carry the same energy they would for a stationary observer. In the reference frame of the spacecraft, particles approaching head-on from the direction of travel appear to be moving faster than they are in the galactic rest frame. Their momentum is boosted by the Lorentz factor, the same mathematical quantity that governs time dilation. At 50% of light speed, head-on cosmic ray protons appear to carry about 2.3 times more energy than they would for a stationary detector. At 90% of light speed, the factor is about 3.6. The radiation environment gets harder as you go faster. The speed you need to cover interstellar distances in a reasonable time directly worsens the radiation hazard. This is a fundamental physical trade-off, not a technical limitation that better engineering can overcome. Going faster reduces travel time. Going faster also increases effective radiation dose rate. The two effects are linked by the same relativistic physics. There is no velocity at which both are simultaneously optimized. There is only the management of the trade-off within the constraints of whatever shielding is practical, for whatever mission duration is acceptable. And the biological effects of time dilation add another layer of complexity. A crew member who has been traveling for 40 years at 10% of light speed arrives at their destination having aged 40 years. They've experienced 40 years of radiation exposure, of microgravity, of isolation. Whatever physiological and neurological changes occurred during the voyage, they occurred over 40 years of crew time. There is no shortcut to the health consequences. The crew who arrives is the crew who experienced everything that happened during the voyage, in full, regardless of how much time passed on Earth. That's what it means for the biology to happen in the ship's reference frame. Step back and consider the full scope of what we've covered. The vacuum, an environment that ends an unprotected human in 14 seconds, requiring constant, active, failure-free maintenance of atmospheric pressure for the entire duration of any mission. The Sun, a radiation source whose most dangerous output, solar particle events, can only be partially mitigated, arrives with limited warning and requires specific engineering countermeasures that reduce but do not eliminate risk. Galactic cosmic rays. The accumulated particle output of billions of years of stellar violence, always present, penetrating any practical shielding, accumulating measurable biological damage over months and years, with potential neurological effects whose magnitude in humans remains incompletely characterized. Magnetars. Objects capable of releasing more energy in under a second than the Sun produces in hundreds of thousands of years, with their radiation arriving at the same speed as the information that it's been released. Gamma-ray bursts, the most energetic electromagnetic explosions in the universe, beamed in concentrated jets, detectable from billions of light-years away, with no advance warning possible. Compact object gravity. Tidal forces that can pull biological matter apart at the molecular level in open space, with the most dangerous objects emitting no detectable radiation in their quiescent state. Interstellar medium at relativistic velocities, gas, dust, and macroscopic objects that are negligible at low velocities and lethal at the speeds required for practical interstellar travel. Hawking-like radiation from extreme space-time geometries. A quantum mechanical consequence of horizon formation that places a potential radiation trap inside the physics of the most aggressive propulsion concepts. Dark matter. Gravitationally real, electromagnetically invisible, shaping the large-scale navigational landscape of the galaxy without being directly detectable by any instrument we've built. Microgravity. The slow reversal of biological adaptations that evolution spent millions of years constructing, affecting bone, cardiovascular function, vision, and potentially neurological function over the timescales of a long voyage. Time dilation. Amplifying the effective energy of incoming radiation at relativistic velocities, linking the solution to one problem directly to the worsening of another. These are not hypothetical. Every one has been measured, observed, or rigorously derived from verified physics. They are the actual properties of the actual universe. The universe we live in. The one that exists outside the thin protective layers of atmosphere and magnetic field that every human on Earth relies on, every moment of every day without thinking about it. And we go anyway. We always go anyway. That's the other true thing about this. Astronauts have lived for over a year in low Earth orbit, accumulating these effects in diminished but real form, and returned to Earth, and recovered, and returned to space. Robotic missions have operated in deep space for decades. Voyager 1, launched in 1977, has been traveling through the interstellar medium since 2012. It is more than 22 light-hours from Earth. It still transmits. We still receive those transmissions and interpret them. In one of the most remarkable achievements in the history of engineering, the antennas of the Deep Space Network detect the signal from a 22-watt transmitter more than 22 light-hours away and extract meaningful data from it. We are doing this incrementally, with instruments before humans, with robotic systems demonstrating the environment before we commit people to surviving it, with each mission teaching us things we didn't know, and those things informing the design of the next mission. That sequence is correct. That sequence is the only responsible way to do this. The invisible traps of deep space are not arguments for staying home. They are the specific engineering challenges that separate where we are from where we're going. Each one is a defined problem. Cosmic ray shielding is a materials science and propulsion problem. Solar particle event protection is an architecture and monitoring problem. Interstellar medium interaction is an ablative shielding and active deflection problem. Navigational accuracy is a sensor and computational problem. Dark matter mapping is an observational astronomy and gravitational modeling problem. Microgravity countermeasures are a biology and exercise physiology problem. None of them has a clean solution today. All of them have research programs. All of them have people who have dedicated careers to solving them. Progress is real. Not fast enough to enable crewed interstellar travel in any near-term time frame, but real. Each solved sub-problem makes the larger challenge more tractable. Each mission that returns data makes the design of the next mission better. The timeline to crewed interstellar travel is unknown. It might be centuries. The physics doesn't set a deadline. It sets constraints. And the history of human engagement with physical constraints is that we work on them, systematically, honestly, until we either solve them or find that there's a fundamental barrier we can't cross. So far, most of the barriers have yielded. Not quickly, not easily, but they've yielded. So, the next time you stand outside on a clear night and look at the stars, understand what you're looking through. Not just the dark, not just distance. Radiation, from thousands of sources at energies our best instruments strain to measure. Particles moving at velocities that make the hardest materials we know softer than vapor. Gravitational architectures that bend trajectories across decades of travel. Objects in the dark whose existence we infer from statistical arguments and occasional close encounters. Quantum mechanical consequences of extreme geometries that place hazards inside the most advanced propulsion concepts we've conceived. The accumulated output of 10 billion years of stellar violence, still traveling, still arriving, still interacting with whatever is in its path. The universe is not hostile the way a predator is hostile. It doesn't notice you. It doesn't care. It's hostile the way physics is hostile. Completely. Impartially. Without exception or awareness. By rules that have applied since before the first star formed, and will apply long after the last one goes out. Understanding those rules precisely is how you build the systems to survive them. Understanding them honestly is how you avoid the mistakes that come from underestimating them. And we are, slowly, understanding them. One measurement at a time. One solved equation at a time. One mission's worth of data at a time. That's the work. And the work, as it always has, is going to get us there. Now, step back from the individual hazards and consider the problem of navigation itself. Getting from one star system to another is not a matter of pointing at a destination and accelerating. Space is not static. The stars are moving. The destination is moving. The galaxy is rotating. Dark matter is redistributing gravitational fields in ways that can't be directly observed. And the journey takes decades, during which everything continues to move. When astronomers calculate the trajectory for a spacecraft to reach Mars, they have to account for where Mars will be when the spacecraft arrives, not where it is when it launches. For a 9-month transit, this is a tractable calculation. The orbital mechanics are well understood. The uncertainties in Mars's position at arrival are small and manageable. For an interstellar voyage, the calculation is vastly more complex. The nearest star system, Alpha Centauri, is 4.24 light-years away. At 10% of light speed, the transit takes about 42 years. During those 42 years, Alpha Centauri continues moving. The system has a proper motion, a velocity across the plane of the sky, independent of the motion toward or away from us of about 3.7 arc-seconds per year. Over 42 years. That's about 155 arc-seconds of positional change. In terms of actual distance, Alpha Centauri moves roughly 200 astronomical units sideways relative to its current position during the voyage. The spacecraft has to be aimed not at where Alpha Centauri is, but at where it will be when the spacecraft arrives. This is achievable in principle. The proper motion is well measured, but the accuracy required is exacting. At the distance of Alpha Centauri, even a tiny angular error in the launch trajectory, a fraction of an arc-second, translates into missing the target by an enormous distance. And the spacecraft cannot course correct freely. Course corrections require thrust. Thrust requires fuel. A spacecraft traveling at 10% of light speed with enough fuel to make significant trajectory corrections is a dramatically more massive vehicle than one without that capability, which requires more propulsion, which requires more fuel. The rocket equation circles back on itself. Most practical interstellar mission concepts accept very limited course correction capability and rely on the precision of the initial trajectory. This means the launch trajectory must be computed with extraordinary accuracy. It means the launch system must execute that trajectory with extraordinary precision. And it means that any perturbation during the voyage, from gravitational influences not fully accounted for, from radiation pressure from nearby stars, from drag in regions of the interstellar medium that are denser than expected, accumulates as trajectory error. Small errors early in a 40-year voyage become large errors at the end. A navigation error of just one part in 100,000, sustained over 40 years, translates into a positional error of several billion miles at the destination. In the context of a planetary system 4 light-years away, that's the difference between arriving in the right place and arriving in completely the wrong part of the system. The precision required for interstellar navigation is not impossible in principle, but it requires knowing the gravitational landscape between Earth and the destination with far more precision than we currently have. It requires instruments sensitive enough to measure trajectory deviations on timescales short enough to correct them. It requires communication with Earth to receive updated navigation data that works across light-year distances with information delays of years. If you send a course correction message from 4 light-years away, it takes 4 years to arrive. The acknowledgement takes 4 more. A round-trip exchange of navigation data takes 8 years. During those 8 years, the trajectory error that prompted the message has continued to accumulate. The correction, when it's finally executed, is based on information that's 8 years old. Deep space navigation is an entirely different problem from anything we've solved before. Not harder versions of the problems we've already handled. Qualitatively different problems requiring qualitatively different solutions. Consider what communication itself means across interstellar distances. At the distance of Alpha Centauri, 4.24 light-years, a radio signal takes 4.24 years to arrive. Send a message from the spacecraft. 4 years later, Earth receives it. Earth sends a response. 4 years later, the spacecraft receives it. A single round-trip communication takes 8.5 years. For a crew on a 42-year voyage, that's roughly 5 complete communication cycles from launch to arrival. You could ask a question when you launch and receive the answer somewhere around year 9. You could report an emergency and receive guidance approximately 4 years later, by which time Whatever the emergency was has either been resolved or the crew is gone. The communication delay isn't just inconvenient. It fundamentally changes the nature of mission operations. Mission control on Earth cannot manage an interstellar mission in real time. The crew is functionally autonomous from the moment of launch. Every decision made during the voyage is made by the crew based on their own assessment, with no ability to consult with experts at home except on questions where an 8-year round-trip delay is acceptable. The implications for crew selection, training, and psychological support are substantial. The crew must be capable of making every medical, technical, navigational, and scientific decision independently. They must have the knowledge, the judgment, and the psychological stability to do this for years or decades, with minimal external input.